Hello everyone, welcome to SPEC eLearn, the online learning channel dedicated to chemical engineers. Chemical Reaction Engineering, Part 5, Reactor Engineering. This video focuses on reactor engineering related to catalytic reactors. In this video, you will learn what is reactor engineering, what are the important parameters to be considered in selecting and designing reactors, the type of reactors, and the general design equations. I would appreciate if you subscribe to the channel, which is striving hard to deliver valuable knowledge content for your career progress. So subscribe now before you forget. Reactor engineering refers to design and development of reactor hardware for meeting the desired reactor performance. Reactor engineering plays a key role in petroleum and chemical processing. Reactor selection and design is the basis of economical and safe operation. The reactor design and operational considerations include size and shape of the reactor, batch, semi-continuous and continuous, heat transfer requirements, deactivation, regeneration or replacement of catalyst. The reactor performance is analyzed in terms of conversion, selectivity, catalyst activity, catalyst life, stability, controllability, safety, and environmental issues. These performance parameters are important design considerations in catalytic reactors. The choice of the reactors is guided by these parameters. Having understood the base of design of catalytic reactors, let us now move on to have a look at the type of catalytic reactors. The first step in the reactor engineering is to select the suitable reactor type. Catalytic reactions usually involve multi-phases: gas liquid, gas liquid and solid, gas and solid. Gas liquid reactors include stirred reactors, packed column reactors. Gas liquid solid reactors include stirred slurry reactors, trickle bet reactors. Gas solid reactors include fixed bed reactors, moving bed reactors, fluidized bed reactors. Now let us look at the engineering approaches for these reactors. There are a variety of ways one can bring these phases into contact for reactions. The generally followed design approach consists of 1. Catalyst design, 2. Gas and liquid injection and energy addition or removal methodology, 3. Choice of hydrodynamic flow regime. Let us look at these design strategies one by one. First, catalyst design. Gas liquid reactors. You can have a gas dispersed system or liquid dispersed system. Gas solid reactors. The important approaches are catalyst size, catalyst shape, pore structure of the catalyst, the distribution of the active material in the catalyst. Next is the reactant injection strategy. The reactors can be of batch or continuous type. The contacting flow pattern, it can be of co-current type or counter-current type or cross-current type. Product separation, it could be in situ or separate activity. Heat addition and removal strategies. Heat addition is required for endothermic reaction. One of the methods of adding heat is in a furnace, which is a fired heater. Heat removal method for exothermic reaction. It includes interbed heat exchangers or gas quench. Another method of heat removal for exothermic reaction is to install external heat exchangers for heat removal. Another strategy to be determined during the design stage is the hydrodynamic flow regime for operation. The hydrodynamic flow regimes include packed bed or fixed bed reactors, trickle flow or pulse flow or spray flow or bubble flow, and riser transport as in the case of FCC. Having discussed the design approaches for catalytic reactors, we will now look at some of the examples of real world reactors where these engineering approaches have been adopted at the design. First, let us look at the examples of heterogeneous catalytic reactors. The first among the heterogeneous reactors is fixed bed reactors. Fixed bed catalytic reactors fall into two types, categorized based on the reactor orientation: vertical fixed bed reactors and horizontal fixed bed reactors. Vertical reactors is usually the choice when it comes to selecting the reactor type. Most of the industrial reactors in fertilizer and petrochemical industries are vertical reactors. Vertical orientation ensures uniform flow through the fixed bed without any bypassing and dead flow spots where they can accumulate and impact the reaction results. Vertical reactors need less space. They are suitable for mixed phase flow like trickle flow. Illustrated in this figure is a vertical reactor, a fixed bed Kellogg ammonia synthesis process. This is a 4-bed catalytic process with a downflow. Due to exothermic nature of the reaction, cooling of the reactants intermediately is required that needs a multi-bed reactor concept. Multi-bed design with intercooling with cold fresh feed gas or quench will reduce the average bed temperature and optimize the conversion. Another vertical fixed bed reactor technology is tubular reactor. The engineering approach of this reactor technology is different from the one we just discussed in that it is an endothermic reaction. Reaction is favored by high temperature. As the reaction proceeds and the fluid flowing down the reactor, the temperature drops. Hence, heat needs to be added. A vertical row of tubes are placed in a furnace and heat is supplied by firing. Usually, it is downflow reactor. The number of tubes, tube diameter, the tube length are the design parameters. Horizontal reactors are wide but relatively shallow. The gas flows down from top to bottom. They are selected to minimize very high pressure drop associated with high GHSB, that is for large capacities. Illustrated in this figure is a fixed bed adiabatic horizontal catalytic reactor, internally refractive lined and externally insulated. The next important reactor technology is fluidized bed reactor, riser transport. The figure shown here is a fluid catalytic cracking unit. FCC units are widely used in refineries to produce higher value gasoline from gas oil. FCC units basically consist of two units: a reactor in which hot catalyst is brought into contact with feed, which is the gas oil, and a regenerator in which the coke deposited in the catalyst is burned off for regenerating the catalyst. The riser is an important part of the FCC. The conversion of heavy petroleum fraction occurs in the riser reactor, which is a long tube length of approximately 30 to 40 meters with proportionately small diameter, roughly 0.8 to 1.2 meters. After complete vaporization of the hydrocarbon feed, the two phases, solid catalyst phase and vapor phase, which is the hydrocarbon and steam, are left in the riser. Catalytic reaction occur in the vapor phase. The decrease of density of the gas phase due to cracking and the expanding volume of the vapor that are generated are the main driving force, that is increase in velocity to carry the catalyst up the riser. Catalyst and products are quickly separated in the reactor. The product leaves the reactor at the top. The separated catalyst is drawn to a regeneration unit where it is contacted with hot air to burn off the coke, and the catalyst gets regenerated. The regenerated catalyst is circulated back to the reactor again with a small amount of fresh catalyst. The heat is transferred from the catalyst phase to the gas phase. Temperature of the gas phase increases due to the heat gain, and the catalyst decreases due to the heat loss. The reaction kinetics, hydrodynamics, heat and mass transfer, and catalyst deactivation are the important design performance parameters. The heat transfer between the phases play an important role in the catalytic cracking of the hydrocarbons. Another widely used reactor technology is a moving bed reactor (MBR). Shown in this figure is a moving bed catalytic reactor. Note that the rows of perforated tubes are installed vertically in the reactor. The catalyst particles enter at the top end of the tube and moves down, while the gas enters radially through the perforations in the tube. After reacting with the catalyst, the gaseous products of reaction moves out of the tube and leaves the reactor at the top. The advantages of radial type MBR is low pressure drop across the bed length and better temperature control in highly non-isothermal reaction. Moving bed reactor can also have other flow arrangements such as parallel flow and countercurrent flow. Moving bed reactors with parallel and countercurrent flow are used in hydrotreating processes such as hydrodesulfurization, hydronitrogenization, and hydrodemetallization. Another widely used type of reactor is a trickle bet reactor. Shown in this figure is a trickle bet reactor used in the hydrotreating of petroleum products. The reactor is of fixed bed type. Like in packed mass transfer column, the liquid and gas mixture is distributed over the bed. The liquid trickles down the bed while the reaction is in progress. The catalyst provides the surface for reaction between the gas and the liquid. Due to exothermic reaction, multi-bed quenching technology is required. Before we move to the next type of reactor technology, let me throw some light on the hydrodynamics of the flow regimes when a liquid and gas flow over a solid surface. When gas and liquid flow over a bed, four flow regimes are usually observed: trickle flow, pulse flow, spray flow, and bubble flow. The flow regimes are influenced by the packing density, liquid gas flow rates, density and viscosity of the fluid. Trickle flow occurs at low liquid and moderate gas flow rates. The gas is continuous phase and liquid is discontinuous phase. Low pressure drop and suitability for foaming liquids are the advantages of trickle bed flow regime. Pulse flow occurs at moderate liquid and moderate gas flow rates. Both gas and liquid are in semi-continuous phase. Spray regime is observed in very high gas rates and liquid rates. Gas phase is continuous and liquid is a dispersed phase. Bubble flow occurs at high liquid rates and low gas rates. The liquid is continuous phase and the gas is dispersed phase. Having seen the different types of heterogeneous reactor, we will move on to see an example of homogeneous catalytic reactor. Shown in this figure is a batch homogeneous catalytic reactor. Catalyst with some starting reactant is fed initially into the reactor. The second reactant in the liquid phase is continuously fed and agitation is maintained during the reaction. The reaction product is circulated by a pump externally through an exchanger to remove the heat of reaction continuously. When the required batch size is achieved, the feed addition is terminated. After that, the product containing the catalyst is discharged from the reactor to another processing vessel where the catalyst is separated. The unique feature of this reactor is the catalyst is in a homogeneous phase. Reactor design complexity. In terms of complexity in design and operation, the fixed bed reactors with slow catalyst deactivation are less complex in design, even with heat effects with multi-bed or quench technology. Examples include ammonia converters, methanol reactors, and naphtha reformers. Fixed bed reactors with fast deactivating catalysts such as propane dehydrogenation reactors are comparatively more complex than the other fixed bed reactors mentioned above. This is followed by moving bed reactors, trickle bet reactors, and fluid catalytic reactors in that order of complexity. So far, we had focused our attention on the engineering approaches for designing and selection of catalytic reactors. We will shift our focus to the analysis of catalytic reactors. A unique aspect of petroleum refining is that the streams are mixtures of thousands of compounds. It is not possible to work with mole basis as is common with other simple industrial processes. Hence, mass basis is frequently used for reactor design equations. Instead of contact time, reciprocal space velocity is used. In batch reactors and CSTR reactors, the reactants and the products are continuously mixed, and hence there are no concentration and temperature gradients. Conversion is controlled by the feed rate or the reaction temperature. In contrast, in plug flow reactors, which is the most commonly used, it is difficult to measure the reaction rate because the concentration changes with the length, and in addition, there are temperature gradients. The equation for analysis of plug flow reactors are given as follows. As illustrated in the figure on the left, in a plug flow reactor, the concentration is changing with the reactor length. Note, from the initial concentration, the Ca naught, it decreases to Ca at the end of the reactor. Also, the temperature is changing along the length depending on whether the reaction is exothermic or endothermic in nature. The residence time of the species is a function of its position in the reactor. Shown here is the equation for analysis of plug flow reactor. Tau is equal to Vr by V, which is equal to Ca naught integral of dx by minus Ra. Where tau is a spacetime in hours, V is the volumetric flow rate in meter cube per hour. Vr is the volume of the reactor. RA is the reaction rate in moles per hour per unit volume of the reactor. X is a fraction of A converted. Ca0 is a feed concentration of A at the reactor inlet. If the desired conversion of component A is XAF, then the spacetime is obtained by integrating the above equation from 0 to XAF. As the conversion increases, the concentration of reactant A decreases and the reaction rate decreases. For a given feed rate V and required conversion, the above equation can be used to determine the size VR of the reactor. Illustrated here is a plot of minus 1 by RA versus the conversion of reactant A. The area under the curve is tau by Ca0. Now let us come to the plug flow catalytic reactors. The above equation for simple plug flow reactor can be used for sizing catalytic plug flow reactors also. For catalytic reactors, it is usual to express the design equation in terms of the weight of catalyst required rather than the volume of the reactor. It is often the weight of the catalyst that is the design sizing parameter. So the design equation for the catalytic plug flow reactor is WFA0 equals integral of dx by minus r dash a. It can also be expressed in terms of weight hourly space velocity. 1 by WHSV equals integral of dx by minus r double dash a. Where W is a weight of catalyst, X is a fractional conversion of A, FA0 is a molar flow rate of feed in moles per hour, WHSV is a weight hourly space velocity in gram feed per hour per gram of catalyst, R dash A is a reaction rate in moles per hour per kg of catalyst, or double dash A is a rate of reaction gram per hour per gram of catalyst. For given conversion and feed processing rate, the weight of the catalyst required can be found out by graphical integration of the right hand side of the equation given above. A plot of minus 1 by RA can be made for different values of XA. This is a plot of minus 1 by RA versus fractional conversion in a catalytic reactor. For a given conversion, the area under the graph can be found out. The area under the graph equals 1 by weight hourly space velocity. It's also equal to the weight of catalyst divided by the molar flow rate. The reaction rate decreases as the concentration decreases, and also for endothermic reaction, the reaction rate decreases as the temperature decreases. 1 by RA, the reciprocal of the reaction rate curve, increases as the conversion X increases. As we have seen in the figure, the area under the curve is WFA0 for a given conversion. Since FA0 is known, the weight of catalyst can be calculated from the value obtained above. Please subscribe to our channel and get updates on the upcoming courses by pressing the subscribe button. It will motivate us to produce free, knowledge-rich video content for you. With this, we have come to the end of the presentation. Hope this presentation with narration and animation was useful. Please give your comments, if any, about this course after you finished viewing the video. Share with your friends and colleagues to reach out to a large number of career-oriented professionals and students who are desirous of developing job-oriented skills and enhancing the knowledge base. Thank you for watching.